Hey guys, welcome to another lesson. So today we're going to do a new topic under the extension 2 syllabus. The topic is vectors, and we're going to focus on questions relating to vector equations. So I'm planning about 2 or 3 videos. The first video, your classic questions of proving lines that intersect or are skew, etc. Right? Classic questions. I've got 4 or 5 of them. The next lesson I might do some that interact with spheres, and the third video, if I do it, maybe some interesting questions that have vector equations in there. Now, before I go on, as always, please, if you like the video, give it a like, subscribe to the channel, and tell your friends, right? So let's begin. So we'll start off with a past paper question from Balcombe Hills, right? Classic question. It's a 3 marker. Nothing really hard about this, very textbook. I thought I'd just do it just to get the system going, get the framework going, right? So in this question, we got 2 vector equations, right? R and, well, actually they both are, should be R1, R2, but let's leave it. Both of these explain why these lines are not parallel, right? That's an easy question. It's a 1 marker. All you got to do is basically demonstrate that the direction vectors are not multiples, right, of each other, are not scalars of each other, right? Once you do that, they're not parallel, right? And then determine whether lines are skew or whether they intersect. So then we solve that simultaneously for x, y, and then sub it into z to see whether it's skew or they intersect. So this is as textbook as they come. Maybe part 1 has a bit more. So let me just zoom in, write a bit neater that way. All right, guys. So for part 1, right, we know that the direction vector, I'll call it D1, right, is 1 for the first one, and the direction vector of the second equation is 4, -11, and 3. Guys, when I multiply everything by 4, right, to get the top one, right, so if I multiply that guy by 4 to get the top number aligned, the rest don't multiply. So you can conclude, therefore, right, D1 is not a multiple of a D2, therefore lines are not parallel. Yeah, I don't think they're looking for anything more than that. Quite simple and quite straightforward. Let's move on. So the structure, whenever you're doing skew and intersection of lines, or skew or intersection of lines, just to be clear, right? Whenever you're in a 3-dimensional space, right, you can have 2 lines that go and never touch each other, right? And that's skew. Yeah. Sometimes they'll intersect, right? But in 2 dimensions, you'd always, unless they're parallel, right? Unless they're parallel, you'd always get an intersection, right? So in 3D, it's when if they're not parallel, it can be skew, right? Where they just basically go off in different ways and never sort of cut each other. So in this case, so we always, structurally compare the x values, y values, and z values, right? So I'm just going to go to comparing x, right? You got 2 plus lambda equals to -4 plus 4 mu. Yeah, comparing y's, I got -3 plus 4 lambda. So did I do that right? Let me see. Hopefully, yeah, cool. And 6 minus 11 mu. All right, and then comparing z's. All right, this one I can zoom out a bit just to show you what I'm looking at. And then you get 1 plus lambda equals to -2 plus 3 mu. Yeah, so I'm going to solve this simultaneously, guys. I'm not too wedded to which ones you do. Like, I can sort of see there that this one has lambda, this one has lambda. I'm probably going to solve those 2 first and then sub it into y, right? So maybe from both of these, right? So before I call it 1, 2, 3, I'm just going to simplify it. Yeah, I might make lambda the subject on top. So no. So maybe I'll call it 4 mu minus 6. This one I might go 4 lambda and chuck the 3 on the other side. So what's that? 9 minus 11 mu. And then the last one, I'll make lambda the subject. Chuck the one episode is 3 mu minus 3. Right, now call that number 1, number 2, number 3. Yep, I'm going to use 1 and 2. I said 1 and 3 to solve simultaneously. So sub 1 into 3. Right, and I get, so I'm plugging, right, just to be clear, this guy, let's go, plugging this guy into here, right? And I get, what do I get? Let's see, 4 mu minus 6 equals a 3 mu minus 3. Let's see, mu equals to 3. Right, if I get that, and if I sub it back into lambda, any of these, right, I should get 3 times 3 minus 3 is 6. Right, now once you get both of those, the aim is to plug both of these guys into equation number 2, right? Sub them both into equation number 2. And if the left-hand side and the right-hand side are equal, then you have intersection. If you don't, then you have skew. So sub, maybe I'll call these guys both 4, sub 4 into 2. And you go left-hand side is 4 times lambda, right, which is 4 times 6, 24. And the right-hand side is 9 minus 11 times mu. What's that? 9 minus 33. That looks negative 24, is it? Okay, that doesn't equal. So therefore, left-hand side does not equal to right-hand side. Therefore, oops, I'm at the very bottom. Skew lines. How's that? Nothing too hard about that at all, I think. Pretty straightforward. Hopefully that was okay, guys. Question 1, done. Right? Your classic parallel lines and perpendicular lines, pretty sweet, right? All right, let's have another go. Different question, right? Different question. This one here is from the Catholic School Papers, CSSA. It's got 3 parts, 6 marks. Let's see what we're dealing with here. So the question says, a line passes through 2 points, right? Shaded vector equation, okay, that's pretty straightforward. Vector equation, right? You basically pick one of the points and call it R0, and then from A and B, subtract them to get the direction vector, and you plug it into the second part. Okay. Determine whether this guy lies on the line. Okay, that is, you sub it in, right, and see if it holds, right? All the lambdas and stuff hold. Third one, consider a line with parametric equations of that. Okay, so instead of giving you another vector equation, they've basically just given to you in parametric form, which is nice. And then assume this line's not neither parallel nor perpendicular, intersect or skew. Okay, part 3, very similar to the last question that we did, but part 1 and 2, the build up is a bit different. So let's react to that. So part 1, right? Now remember, the formula for vector equations, oops, is R vector equals R0 plus lambda D, not D1. Yeah, I mean, that essentially is your vector equation, right? That guy there, right, governs your formulae or your structure for vector equations. Once you get that, guys, for this question then, R0 is just the first point, right? So 1, 3, -2. I know they want it in Cartesian. I express it in columns. I'll do it later. And then in this case, direction, we'll keep writing D1. Direction vector would be second point, position vector of the second point, minusing the position vector of the first point. It's -2. And I'm hoping then that becomes what, 4. Wait a second, no, I've done the wrong thing. I've inversed this accidentally, don't know why. Yep, 2 and 5, that's better. Okay, let's do that better. 2 minus 1 is 1. Right, I actually have the answer there, so you can actually see it. And minus 7, perfect. So therefore, once you get that, yeah, r equals 2, and I'll put it back. So you can put it, I'll put it in column form first. 1, 3, -2 plus lambda 1, -4 minus 7. Yeah, and then I'll write or. If they want it in Cartesian form, we put it in Cartesian form, right? Minus 2k plus lambda 1, right? They wanted the lambda 1 there for some reason. Well, I know the reason. There's another equation downstairs, but we'll get there in a sec. So guys, this one here, I minus 4j minus, did that wrong again, right? That's a plus. Man, my simple arithmetic's letting me down. Plus 7k. Okay, beautiful. Oops, supposed to be a box. Yeah, so that's what the question wanted. Give it to them. Yeah, cool. Now I'm just gonna sneakily put this down here, just to buy me a bit of vertical space. Sorry, a bit of space later, right? All right. Determine whether that point. So guys, part 1, hopefully not too bad, right? Once again, I'm going at that with a bit of pace because I don't think that's very textbook, right? Very textbook. So part 2. Show that this point lies on this. So all I got to do is basically equate the, and I'll do it in column form, right? Just easier. Equate this guy 1, 3, -2 plus lambda 1, 1, -4, 7 then. Oh, that should have a 7 there. Yeah, and equate that to the coordinate or the position vector of 3, 4, 9. And then you basically just equate the x, that plus that times that equals to that, right? That plus that equals to that, and that plus that times that equals to that. And then you basically solve it for one, and then you just got to make sure it holds for the other, right? So if I said comparing x, right? I've got 1 plus lambda 1 equals to 3. So from this one, lambda 1 equals to 2, right? So I've got to make sure that holds in the next two, right? And if it holds, then we're sweet, right? So comparing y's, I've got left-hand side equals to 3 plus lambda 1. So that's now 2 times -4. And that equals to what? 3 minus 8 minus 5, is it? Wait, determine if the point lies on the line. Okay. Just very quickly, I can see that it doesn't. Right-hand side equals to 4. Right, left-hand side doesn't equal the right-hand side. And I suspect that's why it's 1 mark, right? It failed on the y. Probably don't need to do the z, sorry. Therefore, point does not. Let me just quickly check that. Yep. Okay, it doesn't. Okay, perfect. Does not lie on the line. Yeah. So generally speaking, you do a bit more work than that. Like you probably they fail on the z if anything, but they failed on the y. So we're just going to move on. Yeah. Is that okay? So you equate it to the coordinate, found that lambda 1 equals to 2, tested the y value when I compared it, failed, I move on. And last but not least, same question as before. So I'm just going to move this guy up here, right? And in part 3. So the only difference is that R1, right? The first one is given to, I'll let that be R1, equals to 1, 3, -2 plus lambda 1, 1, -4, 7. Right, and the second one, right, they sort of already gave it to you. So this one here, if I had to go and convert that to parametric, right, what they really mean is that they say the x value equals to 1 plus lambda 1, the y value equals to 3 minus 4 lambda 1, and z equals to minus 2 plus 7 lambda 1, right? And they're basically saying compare that or solve that simultaneously with this series of parametric equations. So y equals to 2 plus 3 lambda 2, and z equals to minus 1 plus lambda 2, right? So we solve that simultaneously. So set them equal to each other. So therefore, 1 plus lambda 1 was a 1 minus lambda 2, and then 3 minus lambda 4 lambda 1s, 2 plus 3 lambda 2s, that guy, this guy. All right, guys. Now, what can I see? What's fast? Feels like, before I solve anything, I'm just going to simplify this one first. Knock off the 1, so lambda 1 equals to lambda, or negative lambda 2s. All right, feels like my equation number 1. And then I can solve it into either one. Maybe just, call that number 1. I'm not going to simplify that. Call it number 2. Call it number 3. And I'll just sub it. Let's just do it. Okay. So sub 1 into 2. Right. What do I get? Let's sub. So negative. I want negative lambda 2, and I want to sub that into lambda where lambda 1 is. So sub that into this guy. Right. So I get 3 minus 4 minus lambda 2 was 2 plus 3 lambda 2s. What's that? Plus 4. So 3 plus 4 lambda 2, 2 plus lambda 2, and 3. Therefore, lambda 2 equals to 1. No, negative 1. Yeah. And in that case, lambda 1 equals to, let's see, lambda 1 equals to, if I sub negative 1 back into, will be positive 1, right? Now let me just check that. So yep, perfect, right? Now, remember, once I get that, right, that was using 1 and 2, then I would sub that into number 3 to test. Now I have no more space. So what I will do, I'll make a copy, sorry, quickly. Do it this, this guy, upstairs, perfect. All right, let's finish this off. So when I sub it in, I'll go, so sub, if I was to show amazing working out, call this number 4, sub 4 into 3. And I got left-hand side equals to negative 2 plus 7 times, now be careful, lambda 1, so 1 equals to 5. And the right-hand side, if I sub minus 1 plus lambda 2 in, give me 0. Skew? Actually, no, that's not, doesn't matter, still doesn't. No, therefore, left-hand side doesn't equal to right-hand side, therefore skew. Yeah. Guys, once again, very textbook, nothing too fancy about that. Let's do, hopefully that's okay, by the way. Next question, a little bit different, right? Just tiny bit, right? Nothing too drastic about it, but we're starting to see questions that, students that only do the textbook questions, the next one, it's still technically, very, very common in textbooks, but a little bit different, right? So Clara, from 2020 to 2020. So this question, they gave us 2 equations, right? One vector equation there, one vector equation there. And what are they asking? Show that 2 lines intersect. Okay, that's classic what we did before. Find the angle between, and then find the shortest distance from the point to this line, right? Which is the first equation there, right? So part 1, let's play the game. Let's do what we always do, right? Part 1, show that the 2 lines intersect. So I'm just going to go comparing x, 1 plus 0 lambda, Well, okay, that's actually quite easy then, because you find lambda 2, oh, so mu in this case, quite immediately, plus mu. Equation number 2, 0, so plus lambda equals to 0 plus 3 mu. And then third one, 1 plus lambda equals to 0 plus 2 mu. Okay, cool. So now from the first one, before I actually call it number 1, I mean, looks like mu equals to -1. Yeah. And if mu equals to -1, if I said sub 1, sorry, I should call this 2, call this 3, into 2, I get lambda equals to 3 times -1, lambda equals to -3. Okay, cool. Call that number 4. Yep. And then sub 1 and 4 into 3. And go left-hand side equals 1 plus -3, which is -2. Right-hand side equals to 2 times -1, -2. Therefore, left-hand side equals to right-hand side. Therefore, lines intersect as required, right? Guys, once again, nothing too hard about that, right? Pretty predictable, nothing too drastic, very textbook. And that was 3 marks, right? That's actually very good value. So I'm just trying to make space, that's all. Okay, perfect. All right. That was solving simultaneously. They work in this case, so therefore it's intersecting. Now, angle between 2 lines, piece of cake, right? Dot product over the product of the magnitudes, right? So, guys, we know that for part 2, cos theta equals to R1 dot product over magnitude. Sorry, I should say R1. R2. Yep, we know that. So in this question, now when I say dot products, that's the dot product of the direction vectors, right? Yeah, dot product of the direction vectors. Oh, actually, so angle between 2 lines. Yeah. So basically, I just need dot product. I'm just going to use the direction vectors here. So maybe R1, R2 is actually not accurate, right? Maybe I'll use D. Yeah, you don't actually need the whole line, right? You just need, to find like angle between 2 lines, you just need a direction vector. That's all you need. So I'll go D1, D2, D, and D. So in this case, right, what was D1? Let me just write up here. D1 equals to, just so I don't have to zoom up and down. Actually, no, we'll work with this size. D2. Actually, that wasn't D1, is it? No. D1 is 0, 1, 1, and D2 is 1, 3, 2. Nope. All right, so we're gonna work with these ones and go dot product is 0 times 1 plus 1 times 3 plus 1 times 2, and square root of 0 squared plus 1 squared plus 1 squared times 1 squared times plus 3 squared plus 2 squared. So cos theta should equal to what? 3, 5 on top of a square root. What's that? 2. That's 1, 9, 14. 2 times 14, is it? 2 times 28. Yeah, I think 14 times 2. Yep. So then inverse cos that, I think the angle is 19 degrees and 4 minutes. Guys, nothing hard about that, right? Hopefully nothing hard about that. But I think actually saying that, the only part that students may get wrong is that they don't use the direction vector. They get stuck. They're like, Normally when I do this question, they give me, the vectors. But in this case, they gave me the vector equations. All that does is it means that I got to use a direction vectors because that is a vector in the direction that sets the angle, right? So direction vector is probably the key there for some students that fall short, right? Next question, find the shortest distance between now. The words shortest distance, the phrase shortest distance, some other questions, you'll see this quite commonly. They use perpendicular distance, shortest, same thing, right? All it is, so if you diagrammatically depict any sort of vector, so for part 3, if you depict any vector, right? In this case, the vector is R1, which is 1, 0, 1 plus lambda 0, 1, 1, right? And there is a coordinate somewhere in space of 1, 2, 0, and they want the shortest distance, right? Which is always the perpendicular distance, right? Yeah. So this is how I'm going to do it, right? So if they want this distance, first thing I'm going to do is, right? Now I'm just going to assume this point here. See 1, 0, 1. That's R0. I'm going to assume 1, 0, 1's over here, right? So this coordinate here is 1, 0, 1. Right? Why? Because I'm going to use that to derive. Now I'll try to use colors to demonstrate this, right? I'll use blue as well. Firstly, I'm going to find the vector that gets me here, right? So maybe I'll call this one R, right? Yeah, because it's like R0, yeah. So I'm going to find that vector there, and then, so step 1, find that blue vector. Step 2, find the projection of the blue onto the black, right? So find the green, and then I can find pink. Once I find pink, then I will find the magnitude, right? So the steps are find blue, find green, find pink, magnitude. So 4 steps, 3 marks, 4 unit. It's not too bad, right? So step 1, let us find the vector RP, right? So RP equals 2, right? 1, 2, 0 minus 1, 0, 1. What's that? 0, 2, -1, right? Just to confirm that, perfect, right? That is my blue vector. Now I need the vector projection, right? This guy here, right? This guy is the projection of RP, onto R1, right? That's what it is, right? So let's find that. Projection of RP onto R1, right? Equals 2. So I need the dot product between now. What am I dot producting? I'm dot producting this guy and the direction vector, right? So it's dot product of this guy and the direction vector, right? So let's see. Yeah, let me just check that. Perfect. Yep. So dot product of 0 times 0 plus 1 times 2. So I'm just multiplying these guys and these guys, right? Yep. Plus 1 times -1. Okay. And then divided by, now I'm projecting, right? This onto this. So then divided by the magnitude of the original squared. And all this gets multiplied. All this is outside of the vector 0, 1, 1. Right? That will give me my projection. Now I feel like I'm going to run into the working out. Oh, that guy there. You know what? For this one, let's start a new question. Oh, sorry, start a new page. So for the old one, let's just delete that. This one, I'm going to delete this. Yeah, there you go. There you go. Well, what? I mean, I got PowerPoint, right? So I got unlimited space. Why am I trying to squeeze it in? All right. So this one just feels like I just need to calculate, right? So the top is 1, and the bottom square 2. All right, so half of 0, 1, 1. Perfect. All right. just to be clear, color coded, right? This guy's my blue vector over here. This guy's my green over here. And now I need to subtract blue minus green, right? To get pink, right? I need this vector because then that's the vector that I want the magnitude. That's the shortest distance, right? So why don't I call the pink vector, I don't know, call it A or something, right? Yep. Oh, distance, let's call it, no, let's call it A, yeah? Let's call it A. So therefore, A equals to RP, right? RP minus proj of RP onto R, right? So it'll be blue minus, just be absolutely clear, blue minus green equals to my pink, right? I need pink, that's the magnitude I want, that's the shortest distance. All right, so blue would be 0 to -1, subtracting green is 0, 1, 1, okay. That's not pretty, but let's see what we got. 0 minus a half is -½ 2 minus a half is 3 on 2. -1 minus half is -3 on 2. Yeah, so that's A, but if you're amazing, maybe factorize a half out. So you get -1, 3, and -3. Okay. Is that right? No. 0 minus a half times 0 is 0, my friends. Oh, God. One of those days. One of those days. 0, 0. Perfect. All right. Got A. I just need the magnitude. So therefore, magnitude of A is bring up the half and square root of 0 squared, 3 squared, minus 3 squared. That is a half times root 18. What's root 18? 3 root 2. 3 root 2 on 2 units. That is the shortest distance. How is that? So in this question, whenever you're doing shortest distance, unfortunately, right, it's a bit of a sort of process, right, where you have to go find the blue, find the projection of the green, using addition or subtraction of vectors, find pink, which is the shortest distance, and then magnitude it, guys. So sometimes some schools call the shortest distance perpendicular distance, same thing. That's how you do it, right? Normally 2-3 marks, I'd say 3-4 marks, but 2-3 marks in a 4-unit paper. That's how you do it. Next question, I've got 2 more, right? It's a bit different, right? Now we're doing a bit different. So next one's from St. George Girls. 3 marker, right? I don't think it's that hard, but it's just different. Find the point on the line that is closest to the origin. So if you can imagine, right? This is a similar question, right? Very similar question, but because it's the origin. So this is R, that equals to 1, 4, 6 plus lambda 2, 1, 1, right? Now the origin somewhere here, right? This is 0, 0, 0. So another way to do it, right? So you can, find the vector blue, find the projection green, and then do it, right? Alternatively, right, just as a different way of doing things, right? What if I call this distance d, right? And I said this, right? Distance formula, right? In space, just like the distance formula in coordinate geometry has, this is distance formula, right? So d equals to square root in 3D, right? So in 3D, that'll be x2 minus x1 squared, y2 minus y1 squared, z2 minus z1 squared, right? So I already have, let's pretend that this coordinate at the origin, this coordinate at the origin is x1, y1, z1, right? And then this guy over here gives me my other coordinate, right? Where x1 equals, sorry, x2 rather, equals to 1 plus lambda, or 2 lambda. Y2 equals to m4 plus lambda, and z2 equals to 6 plus lambda, right? And then I just find the distance formula. Guys, so plug all these into the distance formula and go, therefore, distance equals to square root. These guys minus 0, right? So it'd just be like 1 plus 2 lambda squared, lambda all squared, plus 4 plus lambda squared, plus 6 plus lambda squared, right? Something like that. Yeah. Now, what do I want? Closest, right? So theoretically, it's a perpendicular distance. So I'm going to use calculus to do it. If I square both sides, right, I get this. Yeah. If I now try to find the maximum and minimum, in this case, the minimum, right, of the differentiator, right? So, or we'll see, right? I'll show you. You don't even need calculus. If d squared, let's expand everything, right? So I got 1 plus 4 lambda. You'll see that when you do expand everything, what equation do you get, guys? You will get, you can see it, it is a quadratic, right? And we know that with a quadratic, there is a minimum point if it's a concave up or happy face, right? As I like to call it to my students. Plus, sorry, let me just make sure I don't do any algebraic errors. Collect your like terms, so d squared equals to what? 1, 2, 3, and 6 lambda squared. Everything's positive, eh? 4, 8, 12, 24, 1, 16. Is that 52? 53, is it? Ooh, that looks, yeah, okay. Now, that's a concave up happy face parabola, which has a minimum, which is great. So then I can use calculus or I'll just use the axis, right? So yeah, I know that the axis of symmetry is minus b on 2a, right? Which is also, maybe I got lambda, right? Lambda equals to minus b on 2a, which is going to be minus 24 on 2 times 6. What's that, guys? Minus 2. Sub minus 2 in, you'll get your smallest distance, right? So therefore, yeah. Oh, actually, am I finding the distance? I'm finding a point, right? So then sub lambda, once you find lambda, right, sub that into the vector equation lambda, right? And then you got it. So therefore, yeah, the coordinate would be 1, 4, 6 minus 2 times 2, 1, 1. This will give you, this coordinate will minimize distance, right? 1 minus that, so it's minus 3. 4 minus that. 6 minus that. That's your answer. So technically, you can go and do what you did before, right? And find the perpendicular distance, which is the shortest distance between that coordinate and that line. Alternatively, this method's cool, right? Express the distance squared, in this case, as a quadratic. Minimize the quadratic by finding the axis, sub in lambda, and then you're done. Yeah, nice, right? Guys, I've got one more question, right? Not too hard, right? Just sort of along the same vein of vector equations, right? So Balcombe Hills, 3 marks. Find a unit vector that is perpendicular to both. Ooh, I like these questions, right? Basically, right, if you picture, right, sort of unit, sorry, right past it. I've got position vectors sort of in space, right? And it's like find a unit vector that is perpendicular to both, right? So perpendicular to both. Yeah, something like that, right? Something like that. Find a unit vector somewhere in space that is perpendicular to both. So, where the origin is, obviously somewhere downstairs, right? So, guys, I need to find a unit vector perpendicular to both, like some sort of unit vector here of length 1 that is a position vector that is perpendicular to both. Now, to be perpendicular, that is the key word, right? Perpendicular with vectors, I always tell my students, 99% of the time we're dealing with dot product equals 0. So why don't we do this? Why don't we let the position vector of the intersect, the point that I want, be x, y, and z, right? I don't know what it is. I don't know what it is, right? And I know that the dot product between this guy and both points are 0. So since x, y, z is perpendicular Sorry, I don't know why I'm writing sentences. All right, 3 minus 2, 1, and 1, 4, negative 1. I know that this guy, dot with the first one, should go 0. Now, what that gives me, right, is that 3x minus 2y plus z equals 0. Now, second point. I like this one because it's confusing for a lot of students because there's only 2 equations to solve simultaneously. But the point of this one is not to solve for x, y, and z. It's basically to get 2 equations that give you an infinite set of solutions, and that infinite set of solutions is your line, right? So check this out. And so we're not solving for x, y, and z. Just keep that in mind, right? So the second perpendicular expression. So that gives me x plus 4y minus z equals 0. All right, here's how we're going to go. We're going to try to do, whenever I got three variables and 2 equations, I can't solve it simultaneously. But what I can do is make x the subject, make y the subject of x, and then make z the subject of x, right? So for example, I'll show you what I'm talking about. Equation number 1, equation number 2. Yeah. All right. If I was to solve simultaneously, I can see the z's there. I could just add them, right? Let's add them. So 1 plus 2, and the z's get knocked off. I'll get 4x plus 2y equals 0. So I've got y equals to negative 2x, right? All right, keep that in mind. Number 3. Now, so I made y in terms of x. I need to make z in terms of x as well. So maybe I need to eliminate y's. So why don't I double 1? So why don't I go 1 times 2 and get 6x minus 4y plus 2z equals 0 and call it number 4. And then I will solve that simultaneously with number 2, right? And I can see there, if I added these, the y's would get eliminated, which is great. So number 2 plus 4 gives me 7x, y's are gone, plus z equals 0. So z equals to negative 7x. Now, why did I do that? Because now that tells me, right, my coordinate that I want. My coordinate was x, y, z. X is x, y is now negative that, z is negative that. So I'm going to sub both of these, right, to there, into there, right? So therefore, the coordinate would be x minus 2x and minus 7x, right? Now, why is that important? Because that there, if I factor, what is x? X is just a variable, right? So if I take out x, what's that tell me? It's almost like your lambda, right? It basically tells me there's a vector line in space, yeah, that is perpendicular, and that makes sense, right? So for example, if I drew this line, right, completely in space, there's a whole line in space that is perpendicular to these lines, right, in 3D space. Yeah, that's the equation of that line. Now, what do I want now? I want that line to be a unit vector, right? So all I need is I can get rid of the x, right? Because I can let x equal to 1, right, to start with, and then I basically find the unit vector of the remaining vector, and that's my answer. So for example, right, if I was going to say remove it, but if I let x be 1, right, then my one possible solution, one possible vector that is perpendicular is this. And if I wanted to unitize that guy, make it a unit vector, remember, if this is like A right now, for A hat, right, it's what? A divided by magnitude of A, right? So what's the magnitude of A? Oops, sorry, I'll do it over here. Equals to root 1 squared plus 4 plus 49. What's that, guys? 54, is it? 54. Yeah, once I get that, therefore, wait, what's 50? Does that simplify? 9, that's 3 root 6, yes, cool. So therefore, the unit vector that is perpendicular would be 1 over, or divide 3 root 6 of the vector 1, -2, -7. That is my answer. So just to play that back, when they give you 2 lines, right, that I'm perpendicular with, right, I let my coordinate be x, y, z, right? It's a coordinate right now, but what I find is that when I solve it simultaneously, that coordinate is actually a line, and that makes sense. Because basically in 3D space, there can be a whole line that is perpendicular to those 2 lines, right? In this question then, they want you to find one solution that's the unit vector, right, of that line. So then all I got to do, take almost the direction vector, 1, -2, -7, and then unitize that to get a unit vector. Guys, that's the video. Hopefully, vector equations, pretty good start. So the next lesson, I'm probably going to do some questions that involve spheres, and then see where this topic takes me. If you like the video, hit the like button and tell your friends, and yeah, subscribe to the channel. Thank you.